The digital abstraction. In modern computers, information is generally represented by voltages. For example, when one component needs to communicate information to another component, they are connected by one or more signal wires and share a ground. The first component sets a voltage on the wire, and the second component reads the voltage. Because voltages are continuous quantities, we can theoretically encode an infinite amount of information on a single wire by encoding every possible message as a different voltage. There are, however, two problems with doing this. First, there are many sources of noise that can cause the voltage received by the second component to differ from the voltage sent by the first. Second, there is a limited precision with which we can sense voltages. If a meaning was associated with a precise voltage, our information could easily be garbled, so this isn't done. Instead, to cheaply and reliably process information in spite of such noise, we build digital systems. Digital systems consider ranges of voltages to be equivalent. The most common approach is to map a range of voltages into exactly two values, high and low. By convention, high voltages are generally interpreted as on, true, or the number 1, and low voltages are interpreted as off, false, or the number 0. Voltages between these two thresholds are ambiguous, and digital circuits are designed to make the transition between these two valid ranges as quickly as possible. Noise is tolerated in such systems by ensuring that the range of output voltages produced by a component is sufficiently smaller than the range of acceptable input voltages that noise cannot cause a sender's 0 to be interpreted by the receiver as a 1, or a sender's 1 to be interpreted as a 0. In fact, digital components are designed such that their electrical behavior need not be considered when analyzing their digital behavior. This idea is called the digital abstraction. An abstraction is a mental model that retains relevant details while omitting the less relevant ones. For example, consider a component called an inverter. An inverter's digital behavior is to output a 1 when its input is a 0, and to output a 0 when its input is a 1. While these 1s and 0s are represented by electrical voltages in the circuits that make up the inverter, the digital abstraction permits digital designers to ignore those voltages and consider the inverter solely as a component that inverts its digital input to produce its digital output. Such abstraction layers are fundamental for the building of complex systems. They alleviate the need for anyone to be an expert in the system from top to bottom, and allow each level to be developed independently and at the same time.